When dealing with rational functions that have repeated linear factors in the denominator, the standard decomposition requires a term for every power of that factor. Solving for these constants can become algebraically tedious as the number of terms increases, but there is a more efficient way. Traditional methods involve clearing denominators and solving a massive system of equations or plugging in multiple values for x. As the exponent grows, the complexity of the algebra scales rapidly. Today, we will learn how calculus and differentiation can streamline this entire process. The differentiation method allows us to find specific coefficients by taking successive derivatives of the numerator after isolating the factor. This technique is particularly powerful for finding the coefficients of the lower power terms without solving a simultaneous system of equations. Let's define our terms. In this example, the factor x minus 2 is repeated 3 times. We have 3 constants to find. We call the highest power coefficient, in this case c, the easiest to find using the standard cover-up method before we move to differentiation. First, multiply both sides by the highest power of the repeated factor to isolate the constant. By substituting the root, x equals 2, all other terms vanish, leaving us with our first constant. This serves as the foundation for our next steps. To find the next coefficient, we take the derivative of the simplified numerator expression. Notice how differentiation reduces the power of the remaining factors, eventually isolating the next constant in the sequence. This eliminates the need for complex substitutions. By substituting x equals 2 into our differentiated equation, the term containing a becomes 0. This leaves us directly with the value for b. In this specific case, b equals 0, simplifying our final partial fraction significantly. We repeat the process for the final constant. Taking the second derivative isolates the coefficient of the linear term. This systematic approach ensures that even with very high powers, we are only performing basic differentiation rather than solving high-order systems. Let's try a slightly more complex numerator. Here, p of x equals x plus 2, and we have a repeated factor of x minus 1 squared. We need to find constants a and b using our new differentiation strategy. We start with the highest power. By multiplying by the denominator and substituting the root x equals 1, we find that b equals 3. This is the cover-up value for the most repeated factor. Combining our results, we get 1 over x minus 1 plus 3 over x minus 1 squared. We can quickly verify this by finding a common denominator, which confirms our decomposition is correct and much faster than the alternative. To summarize, multiply by the repeated factor, find the first constant by substitution, then use successive derivatives to find the remaining constants. Remember to divide by the appropriate factorial if you are working with powers higher than 2. This method is a lifesaver when you encounter factors raised to the 3rd, 4th, or 5th power. While substitution works well for distinct roots, differentiation keeps the work linear and organized when roots are repeated. Try this one, decompose 1 over x plus 3 squared. First, find b by substitution. Then, differentiate the numerator to find a. Think about what happens to a constant when you differentiate it. In this case, b is 1 and the derivative of the constant numerator is 0, so a is 0. This shows that the expression was already a single partial fraction, but the method still holds true and confirms the result. You now have a powerful tool for partial fraction decomposition. By using differentiation, you can tackle complex repeated factors with confidence and speed. Practice this technique to master your calculus integration. Generated by Vision Solve AI.